In this video, I want to prove this mathematical identity here, and in particular, it is just the calculation of an integral, which I found to be interesting because it is one of those integrals that I saw in the appendix of one of Feynman's books on quantum mechanics and path integrals. So here we have an appendix with some quote-unquote Gaussian integrals, and they are useful, for example, in the calculation of path integrals, which are fundamental in physics. But never mind, this video is not about the physics. I want to show you in particular the one simple method of how to calculate, in this case, it is the third integral from the top, so it's a3. In other videos, in particular, in under other videos on the double slit experiment explained by means of path integrals, I used the result that you see here, a2. It is the second integral from the top, whereas the first one at the top is the simplest one because it is just a Gaussian integral, the usual Gaussian integral. But never mind, in this case we will focus on the third one from the top, which is quite interesting because you can see that apart from the quadratic term inside the argument of the exponential, we also have a term which is proportional to, actually inversely proportional to x squared, so it is proportional to x to the minus 2, if you want. This term here, which is reminiscent of some potential interaction between particles, for example. But I don't want to get into the physics here. I just want to get into the mathematics and show that this result is actually correct. And I will show you just by means of a simple method, a very simple method, without resorting to fancy mathematical theorems or formulas. We will derive this expression in a simple manner. We have to know how to calculate Gaussian integrals, but the derivation will be quite intuitive, quote-unquote intuitive. I also tried to see if ChatGPT is able to solve this integral. So I attached a screenshot or a picture that you see here to one of ChatGPT's chats, and I asked the ChatGPT to solve the integral. And the solution is, let's say, quite a formal solution, because you can see that ChatGPT resorts to Henkel-type integrals, and I don't really like the solution, but the final answer was actually correct. So if you check this final answer, it is the same as the one that we have here. So it seems different because, for example, here you can see that we have this square root of I, and ChatGPT uses this e to the I pi over 4. But if we write I as e to the I pi over 2, well, the square root of this is the square root of this. In simple, I mean, just let's discard all the technicalities behind this reasoning. I just want to show you some simple math. Of course, you have to know complex numbers, but if you take the square root of this, you have e to the I pi over 2, and the argument is multiplied by 1/2. So this is equal to e to the I pi over 4, which is exactly the factor that you see in ChatGPT's answer. And this factor of 2 outside of the square root, of course, can be brought into the square root, and it becomes a factor of 4 here, but all the rest is the same. Also, we will assume that a and b are real and positive, and you will see why in the derivation that I will show you in a moment. But I don't want to derive the answer just like ChatGPT did, by making a substitution in the integral and then recognizing this integral as a form of the Henkel type integrals. And I don't want to do that, because you have to know what Henkel type integrals are, and still you have to know some theory behind them, and of course this is related to complex analysis. So complex analysis or complex calculus is behind what we see here, but the derivation that you will see in a moment is something that, of course, belies or is behind what you see, what you call complex calculus, but we will not see any application of theorems like the residue theorem and so on. So we will just resort to the theory of Gaussian integrals, and for example, we have to know how to calculate integrals of this kind. Integral from minus infinity to plus infinity, e to the minus x squared, and if you want here, you can have a constant, positive constant if you have a minus here, dx. You have to know how to calculate them, and these kind of integrals can also be extended if instead of having a minus, you have an imaginary unit. So in order to understand this perfectly well, of course, you should have some background in complex calculus or complex analysis, because you can use the residue theorem to prove how to, I mean, to calculate such an integral. And I have done that on several occasions, but I will not do it in this video. But I think that the derivation will be quite intuitive if you try to extend your notions of Gaussian integrals. Anyway, so let's stop the talking and let's start doing the actual stuff, the actual calculations. I will start from this expression here. Of course, this is the starting point, and let's rewrite it. So we have an integral from 0 to infinity, and then we have the exponential of ia over x squared plus ibx squared dx, and this is equal to, so now I will rewrite the argument of the exponential by adding and subtracting the same term. So here I have these two terms. Then I will subtract the square root of ab multiplied by 2 outside of the square root, and then I have, of course, to add the same quantity. So I square root of ab, and then I have to multiply this by 2. So this is very simple algebra. There is nothing mysterious about it. Of course, you see that when I add the square root of ab, we have to be a little careful, and that's also the reason why that in here you see that a and b are real and positive. So it will simplify all the reasoning if we can just assume that a and b are real and positive, and of course you can easily take the square root there. Otherwise, you encounter problems if you for example assume that a and b can be negative, or they can even be imaginary quantities. And the problem is that if you have imaginary quantities, of course, with this factor of I, you might have real quantities arising from this product between I and the square root. But we assume that indeed there is nothing imaginary contained in the expressions that multiply the imaginary unit. So all these quantities are real, and for them to be real, of course, we need A and B to be positive, right? Or non-negative. But if they are zero, if we assume that A or B are zero, then we are approaching some limit cases, and we might try to understand what's going to happen in limit cases, but I will not do it here. So I will just think that A and B are just greater than zero. Okay? So this is the starting point. And why did I subtract this quantity and of course add it? Well, if I subtract this quantity, you can see that this expression here, these three terms, form a square, because that's exactly I multiplied by the square of the square root of a divided by x minus the square root of b multiplied by x. And so, of course, we have to square it. So if you square this and multiply it by I, you get exactly this term, right? So at this point, you can factor out the exponential of 2I square root of AB, and then we have an integral from 0 to infinity of e to the I, and then we have square root of a over x minus square root of b times x squared dx, like this. Now let's focus on this integral here. So in particular, let's do a substitution. So the substitution will be the following. We set x equal to minus the square root of a over square root of b multiplied by 1 over y. So if I do that, I can rewrite the integral like this. So we have an integral, and then we have e to the I. And then this term, square root of a over b, if you do this substitution, you get minus the square root of b times y, right? And then we have plus the square root of a over y squared. And then here we have the square root of a divided by the square root of b, and then we get the differential of minus 1 over y. So I have written it like this. So in principle, in this case, the limits of integration are the same, because this expression here, minus 1 over y, is proportional to x. And the proportionality constant, this proportionality constant here is just greater than 0. So the limits of integration here will be the same. And it's quite easy to see that. But the peculiarity about this integral, so here, so far, it seems like a simple substitution, right? But the peculiarity of this is that the argument inside the exponential, the complex exponential, if you check, is formally equivalent to the one that we have here. So this is just a symmetry inside the argument of the exponential, right? They are exactly the same. The only difference is that we call the variable of integration y. So the variable of integration is y, or if you want, in this case, it is just minus 1 over y, because I have kept the variable of integration inside the differential. So this function is inside the differential. If you want, you can write it as dy over y squared. So you can factor out this y squared, but I want to keep it in this fashion because it will be convenient in the following. Now, at this point, we have shown that this integral here is equal to an integral of this kind. And if you want, we can change our variable y back to the variable x, if you want. And let's do it. So we have an integral from 0 to infinity e to the I square root of a over x minus square root of b times x squared dx. This is equal to the integral from 0 to infinity e to the I, and then here we have the same thing, square root of a over x. So I am going to write this first and call, so instead of y, I replace x, minus square root of bx squared. Then we have a factor of square root of a over square root of b, but let me just write 1 over square root of b, and then I will put the square root of a inside the differential. So I have minus square root of a over x. In this case, I have to write x, right? Now, if I multiply the integral on the left by 2, of course, I also have to multiply the integral on the right by 2, right? That's simple math. But instead of rewriting the integral on the right, and multiply it by 2, I can simply rewrite it by adding the integral that I have on the left, in particular in this fashion, integral from 0 to infinity e to the I square root of a over x minus square root of b times x squared dx, because we have shown that the one on the right is equal to the one on the left, right? So since they can be written in a different fashion, but they are still equal, I can rewrite twice the integral on the left as the sum of these two. Simple as that. But we can also rewrite them as just one integral, because I can put this integral together with the one that we have here on the left. And in particular, you see that this argument this integrand is the same apart from what we have here. So that said, I can simply rewrite the differential that we have here like this. I can add the square root of b times x. Why can I do that? Well, because you can see that if I take this differential, of course I have the differential of minus the square root of a over x, and then I have plus the square root of b times the differential of x. So the square root of b will cancel the square root of b here, right? Simple as that. And therefore, it's quite easy to see that we get back what we just wrote a second ago, right? But this is actually very convenient to rewrite it like this. And why is that? Well, because now we can make another substitution. For example, we can call this t. And of course, you can see that the argument that we have inside the differential is almost the same as this one. It's minus that one, all right? But since this is a square, we can also change the sign if you want inside the square. So we can either change the sign here, or if we change the sign here, we have to put a minus outside of the integral. So let's leave things like this, and of course, if we leave things like this will become minus t. Okay, and if I let t actually x, if we let x go to 0, you can see that this expression here goes to 0, and this will become infinite. So we have an integral from infinity to when x goes to infinity, this term goes to 0, whereas this term here goes to minus infinity due to this minus. So we have an integral from infinity to minus infinity. Remember that we have this minus sign, so I can factor out the minus sign. I can also factor out this 1 over the square root of b, and then I will be left with e to the I t squared, and then I have dt. Now, at this point, it's convenient to put this minus sign inside the limits of integration, and if we do that, this will become a plus, and I simply have to swap the order between the limits. So I have minus infinity to plus infinity. And now you can see that we have found a Gaussian integral that can be evaluated. So there are technical ways to derive the solution, to prove the solution, but I will simply show you an easy way to do that. In particular, if we have an integral from minus infinity to plus infinity of e to the minus x squared divided by 2 sigma squared dx, this is just the integral, the ordinary Gaussian integral with zero mean, and the result of this by simple multivariable calculus can be evaluated to the square root of 2 pi sigma squared, where sigma is the standard deviation of the Gaussian distribution, or sigma squared is the variance of the Gaussian distribution. One can show that this result can be generalized if sigma squared is imaginary. So this requires some complex calculus, and I have provided I provided a proof for this in other videos. I don't want to get into the technicalities behind here, but it can be shown that even if sigma squared is not just a positive quantity, but also an imaginary quantity, this formula still holds. And therefore, if we compare the two integrals, we have to set minus 1 over 2 sigma squared equal to I to find the solution to this integral here. So we can see that sigma squared must be equal to minus 1 over 2i, and this can be written as I over 2. Therefore, the result for this would be 1 over the square root of b times the square root of 2 pi times sigma squared, which is I over 2. So we can cancel this, and we get the square root of pi I divided by b. And remember where we started. So we started from where is it? From the integral that you see here multiplied by 2. I don't know why I don't see the factor of 2 here. Maybe I just inadvertently or accidentally canceled it, but remember that we have a factor of 2 here. So if we want to get the result of this integral, we have to divide both sides by 2. So we divide this by 2, and therefore here we get a factor of 1/2. And if we keep track of the factor of 1/2, of course, here we have a factor of 1/2 as well, multiplied by this. Here we have a factor of 1/2. And if you want, you can put the factor of 1/2 inside the square root as a factor of 4 in the denominator, like this. And therefore, what we get, remember where we started from here. So the result of the integral is just e to the 2I square root of AB, which is just a phase factor that was factored out of the integral because it does not contain any x, so we don't have to integrate over this. This could be factored out. And finally, we have to multiply that by this. So we have the square root of pi I divided by 4b, right? And if my memory serves me right, it's exactly the result that you see here. This is the third integral from the top, and we proved it, in my opinion, with a simple method, without resorting to complex calculus or Henkel type integrals. So I thought that this was an interesting integral to show.